Okay, so on this guy here, right? So start out with the saying Carrie made a 6-sided die in her ceramics class and rolled out 90 times to test if each side was equally likely to show up. Okay, so, and then you have a table here that summarizes the outcome. So with this, again, with thinking of this, dealing with your goodness of fit test in this setup, right? You're looking at a one categorical variable, right? So we're just looking at one roll or one dice, I'm sorry, to see the side, you know, what comes up, right? As far as how that plays out. So with this, that's what they're looking at for the hypotheses. So in fact, dang it, hang on one second. I'm gonna share my screen differently. Let me do that. All right, you see my screen and everything, right?
Yeah.
Okay. Just want to make sure. So I'm going to pull up the actual PowerPoint here because with this, again, this is talking about, you can see the PowerPoint?
Yeah, I can.
Okay. Just make sure it's popping up for you. Okay, so with this one, again, it allows you to determine the hypothesized distribution and it seems valid. So with this one, we're going to look at dealing with these as far as do the goodness of fit test, determining, like an example here, they want to know if the milk chocolate candy's distribution is correct or it's not correct. So that's the big thing we're looking at here with this die, right? When we're rolling it, we're wanting to see if it's going to be equally sided as far as the weight and everything is a fair die or it's not a fair die. So with this, see if this will write for me here. So for your null hypothesis on this setup, you want to say that, well, what's your probability of rolling a 6-sided die?
1/6.
There you go, exactly, right? So we're wanting to say that the claimed distribution, so we can write that even, claimed distribution of 1/6, right? We'll say 1/6 probability. Let's abbreviate probability there. So I'll write so much. We'll claim distribution of 1/6 probability is true, right?
Yeah.
That's what Carrie is wanting to say, that they've got a equally sided die and it's fair to everybody. The alternative then would just simply be that the claimed distribution is not true. In other words, you can even say the alternative hypothesis is that it's an unfair die, right? So that's the big deal with that. Oh, I hate this. Making my hey look kind of crazy. There we go. All right, so that's also one you take away from there is understanding the big setup there for when you're doing a goodness of fit test on this. You're looking at dealing with, you're stating that it's good or it's not good. In essence as well, not just going off the PowerPoint so much, but even if we looked at, looking at the PowerPoint, looking at the big ideas overall, right? The hypotheses are always going to be, are always going to be labeled in this setup here, right? Your null is going to be saying whatever context of the problem is true. Your alternative is saying it's not true. So that's how you're going to go about doing this every time we're dealing with a goodness of fit test, okay? For the chi-squared setup. Now, calculate the expected count of each of the possible outcomes. Well, with this, right, we know the probability you told me was 1/6, right? So we know that we have a 1 out of 6 chance. Well, in this case, then, how many rolls did they say they did?
90,
right?
90 rolls.
Yeah, we rolled it 90 times. So with this, to get your expected counts for these, in this setup, you take the probability times the sample size. So with this, 1/6 times 90 should equal 15. So in other words, what that's saying is if it was a perfect world and you rolled that die, you know, you should 90 times, you should get 15 number ones, 15 number twos, 15 number three, all that good stuff, right? In a perfect
Yeah.
world, that's not going to technically happen, shall we say? I mean, that's just the random and chance probability with that. But in a perfect world, that would work out for us. Again, that goes back to with this, looking at right there for the expected values, it's saying your probability for each category. So in this case, each category, each number, right, in this case, on the side of the die, shall we say, had a 1/6 probability of getting chosen. And we did a sample size of 90 in this case. So therefore, that is how you're going to calculate your expected values every time. So that's a big thing to take away from that. So therefore, you'll know, because when we get down here to this chi-squared test and calculating our chi-squared value, you'll definitely need to know that expected value, because it's definitely a big key part to the equation. In which case, we're going to do in part C here, right? So I want you to calculate that chi-squared test. Hang on a second. Excuse me. All right. So now this kind of gets a little, I guess, shall we say, tedious in the fact of if you have a lot of numbers you got to work out on this, but they've only got 6 for us, so it shouldn't take us too much to write out. So you don't technically have to write it all out either on the test, okay? But as long as you can show the process and what you're using, like with your initial value and your last value, and then have your equal sign, that's all you really need to show. It's just as far as you can check off that you understand what to use and what equation. So in this case, as we saw in our big ideas here, we're going to use this, our sigma, right? The sum of all these, saying our original value minus the expected squared divided by the expected. And you're going to do that for each one and add them all up. So this one, the easiest way you can write this out is, we already know our expected. I'm just going to write it up here, just an E. We know the expected is 15. So now, if we're going to use that equation of original minus expected squared over expected, all you have to do is simply say, all right, so our first original value, when we did the roll here for the number 1, we got a frequency of 12. So I'm going to go ahead and say we got 12 minus our expected of 15 squared all over, and then again our expected, which was 15. Right, and then you don't have to write out for each one of those. Shorthand notation you can do on this is then put a little plus sign, you know, some dots right there, 3 little dots, and then just do the last one. Say, okay, well, I would do this all the way up to the last one. Would say, for the 6s, we had 15 rolls for the 6, so we had 15 minus 15 squared, and then over 15. Okay, and then you can put the equal sign, and then using the calculator or computer program, whichever one you have to use to get the calculations for that. I came out with 14.4 when I worked this out. You can always double check me on that, but I came out with that value for the chi, I don't know why I'm writing X right there, for the chi-square value. So if you do that setup right there, it's saying it's 14.4 is what I came up with to do those calculations.
Gotcha.
Okay, so that was this, let's see, I guess a third big thing to take away from this. Another key factor in this, because what we're dealing with, is talking about your degrees freedom. So in degrees freedom we've been working with, we're taking the sample size, right, and subtracting 1. That's what we've been dealing with.
Yeah.
Which on this, you'd be looking at it and say, okay, well, we did 90 rolls, so 90 minus 1 was 89. Well, not technically. So with this, the big thing to take away from this, I'm dealing with the goodness of fit test, is now you're worrying about your categories, right? So in this case, we had 6-sided die. So there were 6 possible numbers, 6 categorical values we could have gotten. 1, 2, 3, 4, 5, or 6, right? For the side of the die. So since we have 6 possible outcomes, that's what we would take minus 1. So that's going to be the other big difference here. As far as degrees freedom, right here underneath there, just categories -1. So for part D here, that's what's wanting to know. So again, for your degrees freedom, you're simply taking, oh good Lord, my brain's working faster than my hand. Degrees freedom is your categories -1. So in this case, we had 6 categories. We had 6 different sides of the die -1. So we should come up with a degrees freedom of 5 to do this. Any questions so far? Everything good?
No, that makes so much more sense than what I was trying to do yesterday.
Okay. Now this last part here for table C, I do apologize. I thought I'd upload all these and get this all corrected, but I had forgot. And I had another student in class remind me of this morning. And I uploaded the new tables under the modules in Canvas. So you have the proper A, B, and C tables, the full tables, as well as the actual formula sheet that you will be given on your AP exam, right? That's exactly from AP Central. I uploaded those on there, so therefore you guys can use those to actually get a better representation, because the ones I put up on there were old data value tables, and I apologize. I thought I'd upgraded those sooner, but they're good now.
Yeah.
So the table C that is listed in there, you can use, and we'll go through that in just a second.
Yeah,
But
okay.
I'm also going to show you how to calculate this on an Inspire. Do you have an Inspire?
Yeah, I do.
Okay, perfect. I'll show you how to do that on there as well, because that's the easiest way to do this. So it says here, though, to use table C to find the p-value. Well, we know the 2 things you're going to need to use to calculate this using table C, we're going to need to know our chi-square value, which we came out with 14.4. So we're going to use that. And we know our degrees freedom is 5. So I think I got this table already pulled up. Let's see what's over here. Table C. Okay. All right, so table C here. So first off, looking on the left-hand column over here, we know our degrees freedom was 5. So you can come right here to this number 5, and we're going to look right across here on this row. With looking at that, we said that our chi-square value is 14.4. So we're going to see where that value falls with looking at our degrees freedom 5 column or row right there. So it starts out low, and then we're coming up to, looks like we'd fall in between 13.39 and 15.09, right? So that'd be where 14.4 would fall. So with that, then we're looking up here at the top here in this light blue section. So in other words, those values that our p-value should fall between is 0.02, or I should say 0.01 to 0.02, right?
Yeah.
Somewhere in that value is where that p-value should fall if we didn't have a calculator. Would we still be able to compare to a, excuse me, to our significance level to determine if we reject or we fail to reject, okay? In which case, if you're not given a significance level, right, just going back here a little bit, if you're not given that value, what would you use for your significance level value?
0.05.
Perfect, right? So if we know then based off this, with our p-value being 0.02 to 0.01, that's definitely less than 0.05, right?
Yeah.
So then you can go with that saying of, if the p is low, reject the hoe. So right there off the bat, you know that you would reject the null hypothesis in this setup, okay?
Yeah.
So you could simply say that. So looking back here at this setup is saying, what conclusion would you make? By using the table, again, I know a lot of you guys are not putting this on there. I know y'all are looking at the table, and then some are using a calculator, but right on there, right? You know, table C and p-value between, what was it, 0.01 to 0.02?
0.02.
Right? So therefore, you know right there, that's the p-value you're looking at. And we're going to say, I'm just going to write out that p-value thing and say that's less than 0.05. And then I would say I would reject the null. And if you reject the null, in this case, our null hypothesis was that it's true, right? That it's a fair die. So if we're rejecting that, then you're saying that it's an unfair die then, right? You're siding with the alternative hypothesis. You're saying that that die is not a fair die. And you can simply state that since you reject the null. So die is not fair. You just write out something simple like that. Short to the point, but that's exactly what you're stating when you reject the null hypothesis. Now, if you want to get, if you have a TI Inspire, which is super awesome to make it a lot easier to calculate. Let me get my calculator pulled up here. So with looking at that, we can simply say under menu and statistics, so 6 and then 5 distribution, so menu 6, 5, and then you want to go to the number 8 here for the chi-squared CDF.
Gotcha.
And then it's going to say you want your lower bound and your upper bound. Now, before I get into this, again, you'll notice too, we didn't really put in the big ideas here. I think it's mentioned in the PowerPoint though. Let me check. I'm pretty sure it talks about the curve here. Yep. So on the curve, okay, so they're always going to be right skewed, okay? So it's always going to look like this. You're dealing with a chi-square distribution. So with that.
So no matter what, the lower bound is always going to be 0?
Well, yes. Well, not technically 0. Well, I'll show you what we're talking about here. So let me draw this out real quick. That's where it's going to start, right? So as far as if you draw this, you know, you're starting at 0, right? And that's going looking like that, right? And then in which case, you simply have an x squared, or chi-square, I should say, and your degrees freedom, which we said was 5. Again, that changes how thick this tail is over here. All right, that's what plays an effect there. So again, you don't have to draw the picture to scale, but that's just how, that's what the degrees freedom is changing. So with that, we know that our chi-square value is 14.4. So I'm just going to draw this over here. I don't know exactly where it falls. I'm not going to scale it to the exact amount, but 14.4, I'm going to label it. In which case, we want to find out the value above that tail, right? Because that's going to tell us our p-value to be able to compare it to our significance level. So using the calculator, our lower bound in this case is going to be the chi-square value you came up with. So we're going to put in 14.4. For the upper bound, again, that's positive infinity, right? It's going to go all the way to God knows where. Easiest thing, I just type in there a few 9s, right? Throw a bunch of 9s in there. That's a pretty big number. It'll be good enough. And then degrees freedom, of course, we've already calculated that as far as being 5. Our categories minus 1. So we had 6 minus 1, which gave us 5. And with that, that gives us a p-value of 0.013259. Okay? Now, if you're going to use this and you have this calculator, write it out exactly how it looks in the calculator and label the numbers. So for this, change colors here so it looks a little different. So you can simply say you have chi-squared CDF. Your lower bound was 14.4, label it. Then you can just put positive infinity, it's your upper bound. And degrees freedom was 5, label that. And then you can simply put 0.013, okay? which falls in between what the table gave us, right? The table said between 0.01 to 0.02. Well, 0.013 definitely falls within there, right? So the
Yeah.
table gave us the right answer, and our calculator gave us the exact answer that we were looking for. And again, you would still be able to take that value. Then for sure, you could compare that to your significance level, and you would still say reject the null. The P is low, reject the no. Or I'm sorry, P is low, reject the ho. There we go. I got null and ho mixed all up. All right. So with that, that's what you're looking at on this one. So that takes care of being able to do that. Any questions on that? Everything good?
Yeah, that makes a lot more sense than anything I saw yesterday.
Okay, good deal. So yeah, the big thing with the PowerPoint, it kind of just goes through walking through how to look at the table with dealing with that, how this, the degrees freedom affects the tail. As you can see here, if you have a low degrees freedom 1, that makes that line hug that line very tight, right? It goes down pretty quick. Doesn't even really show it being much of a skewed right. But then as the degrees freedom gets higher, that, shall I say, median kind of goes to the right, and the tail gets a little fatter on the end there. So as the degrees freedom goes up, the tail width gets a little bit fatter under there. So you're going to have a higher p-value with the bigger degrees freedom you got. So that's another thing you kind of put in the back of your noggin there to think about and say, when you look at your values, if it makes sense with what the calculator is giving you or what you're finding on the table. So you can just kind of double check yourself with that. Then the other thing was this was really going through, just make sure you understand that, again, you're taking all the values times 60 to get your expected values and whatnot going with that. And let's see here. What else did it go through? Oh man, it's talking about that, the equation for it. Okay. And then the null and alternative hypotheses. Okay. So now, so with part 2, we're just going to kind of go through doing the state plan, do and conclude with this style problem, okay? So again, reading through this is want to know if Arizona, the weather in Arizona affects the driver's choice of a car color. So Cass, this person gets a random sample of 300 cars in Arizona where they live, and they're wanting to see if the colors are in comparison to what the color distribution of vehicles in North America overall are. Okay, that's what this problem is talking about. So for number 1 here, saying, do these data provide convincing evidence that the distribution of car color in the valley differs from North American distribution? So again, we're looking at your hypotheses. So with thinking about what we just did, right, we're going to say that we either it's the same for your null or it's not the same for your alternative. And so that's all you're having to say here, but in the context of the problem. So with this, for dealing with, let me get so I can write on this one. All right, so let's go. So for our null, we're simply saying that the distribution in, I guess that's Oro Valley, is how you pronounce that? Oro Valley,
yeah,
right?
No idea.
Oro Valley is the same, right? We want to know it is, we're saying that it is the same as North America. Let's put NA there for North America. Okay. For your alternative, we're saying the distribution in this valley is not the same. as North America, okay? Then again, another part we're going to put in here for the state is our significance level, in which case they didn't tell us, so we go with the understood value of our little Jesus fish there, and say it's 0.05. So we got our 5% significance level. Now, in this example here for this problem, they already kind of named the procedure just to kind of make sure you understand where we're going with this. And for the plan, so they named it as far as this is called the chi-square test for goodness of fit. You're taking these categorical variables and comparing them against everything, right? For this whole, in this case, everything is talking about North America. So you're seeing what this one area sample is compared to the overall population of North America. Now, you can do a little shorthand notation of that as well for the name procedure. If you want to do that, the same thing as saying your chi-square, and you can simply write GOF for goodness of fit. You could have simply wrote that right there, and that means the same thing. So now going on with this, again, I believe this falls into, I believe they're all on this setup here, yep. So we'll get our conditions. So first off, we want to check if it's random. Then we're going to check for large counts. In other words, all expected counts are greater than equal to 5. That's another difference to this with the conditions. So with this on this setup, we got those large counts, and then those are the two things conditions-wise we got to look at on this.
Gotcha.
So we're looking at randomness and large counts. So randomness, of course, I'm pretty sure they state up here, right here. So it does a random sample of 300 cards, okay? So for your conditions, you can simply write, you got a random, and I'm just gonna write out random selection of 300. I know a lot of this is just copying down what they wrote in the problem, but as long as you do that, the reader knows that you know what you're looking at and what you're talking about. So I know it's kind of redundant and having to write everything again, but it just makes things a little bit easier. So then our other one was a large counts, okay? So in this case, we need to look at it to see that all the expected counts are greater than or equal to 5. Well, the easiest way to do this is take your lowest expected value, right? In this case, the lowest value looks like would be 2%, right?
Yeah.
As far as the percentage-wise for everything up here, it's like 2% would be our lowest value here. So if we're to do that, again, it's already kind of given there. If you just do the math in your head there, it should be equal to 6. But if we were to simply sit here and say we got 300 and then times our 0.02, you should see that gives you a value of 6, right? Well, 6 is greater than or equal to 5, so that checks off. So that's all we're looking at there. That makes sense as far as going forward with that?
Yeah.
Okay. Now, again here, and a lot of the stuff for the do part, they give you a specific formula and work, everything else. You don't technically need to write out the specific formula on doing the problems, shall we say, on a test or something like that. For right here, just kind of to help you get it ingrained in your brain a little bit, which we've already talked about as far as showing that our chi-square test is simply saying our sigma, our sum. Oh goodness, that's a nasty E. Our sigma is going to be our observed, right, minus expected squared all over our expected. Well, then we need to do that now. But in this case, we're going to need to get the expected for each value, right? Because expected for each one is going to be different because we have a percentage up here, right? Which we'll have to multiply times our total value to actually calculate what the expected should be. So in this case, a little bit of work. You don't have to write all the work out. Of course, in the calculator, you can do it. You'll have to do it. So in the first one here, our observed, let's say for the white car color was 84. So we had 84 minus, now our expected, that was 23%. So you should be able to go in here and say 300 times 0.23. So it gives us 69. So for this expected value, we should have minus 69 squared all over our expected value for that one of 69. Plus, and then you can do the dot, dot, dot. We'll do the last one just to make sure instead of writing all these out. But if we do the last one here, in this case, we're looking at the other color value, right? So we got a 39 and a 7%. So our observed is 39. And then, of course, you probably see it's already 21, but we'll write it. We'll do the calculator for those that don't see right off the bat. So 300 times 0.07. So it gives you a 21 value. So 21, and that's squared all over 21, okay? So again, remember, the reason why our expected changed in this one, each one, is because there is a different probability for each one of those colors, unlike the one we did for the roll of the die, right? The expected for each one of those was always 1/6. So therefore, that's why our expected was always a 15 in our previous problem. However, in this one, for the car colors, there was a different probability percentage-wise for each one of those colors. So the expected for each one of those counts is going to change. So don't let that confuse you and get you all mixed up. That's why those values were changing, okay? Now, when I did this and calculated it out, you can always double check this to make sure I got the right number. But when I put in the calculator, it came out to get 29.92 when I did all those values. So with this, again, the other key thing to do is definitely do a picture. Readers like pictures. It allows us to know that you know what you're talking about. So we know it's a goodness of fit test, so we're going to do a right skewed curve here. And again, label your curve, chi-squared. Now with this one, what is the degrees of freedom? How many categories are we looking at here? Well,
8 categories.
Correct, right? So we've got 8 categories.
7.
We've got the 8 colors, right? So, well, 7 colors total, but then that other that throws in there. So it gives us 8, like you said. And as you just said, you take 8 minus 1, which gives you 7, right? So we got that right there. So in our degrees freedom is 7. And there's nothing wrong either with in your work area. If you want to write that out, saying degrees freedom. Oh, good Lord, I keep putting parentheses after that. I don't know why. Degrees freedom. And you can simply say you took 8 minus 1, which gives you 7, okay? You can just write that out just so therefore you've got it on there. Now, with this, we said 29.92. Well, I'm pretty sure that's pretty far over here. 0 is way over here where we're starting. And so 29 is going to be somewhere over here. So I'm just going to draw a little line, 29.92. And of course, we want to see the area of the curve from that going to positive infinity. So for this, the test statistic, it's wanting you to write out your work that you just did there again. It's just wanting you to label that is 29.92. That's redundant. I know, again, on actual workout for yeah, but on a workout for a test though, like I'm saying, that you don't have to keep writing the same number over and over again. Again, if you show the work and draw your picture, you're golden with all your data values you need to represent and show, because right there the picture gives you degrees freedom and your test statistic for your chi-square value. and shows that you know that you're dealing with a chi-square test right off the bat too, because of the way you draw the picture. Now, for the p-value, you can do this, of course, two different ways, as we've done on a previous problem. You can use a table, and again, if you use a table, write out that you use table C. And with that, so we got 29.92 and degrees freedom of 7. So here, I'm going to come over here and look at degrees freedom of 7, and I'm going to look for a value that's 29.92. Well, the highest it goes on this table is 26.02. So we know that it is going to be between 0.005 or lower, right? And it's definitely going to be lower than that 0.005 just by looking at the table itself. So you can write that. You can say table C and say less than 0.0005, right? Or you can use the calculator, which is the best part to use if you have that function. And 29.92, label it at your lower bound. Infinity is your upper bound. And then 7 is your degrees freedom, label it. And then what did you get? Did you already work it out?
Yeah, I did. I got 0.000098.
So 4 zeros and 98?
Yep.
All right, cool deal. So that is a really small number, right? Basically 0 in essence.
Extremely.
So with that, we compare that to our significance level. Of course, the P is definitely less than 0.05. So the P is low, so we'll reject the null. So with this, again, then your conclusion, then you're going to make a statement. You reject the null, so you're going to say that there are convincing evidence against the null. And so we reject the null and conclude the distribution, shall we say, is not the same as the distribution in in North America. So you're saying that you reject the null and the distribution is not the same as the North American distribution. I'm not gonna write that all out, so I don't have much space here to write out. I don't make it look worse than it already does.
I gotcha.
So in this case then, it's saying on the last part here, it's saying if there is convincing evidence of a difference in the distribution of car color, perform a follow-up analysis. Okay, so we would have had to go here and actually list out all of the expected values, which I didn't do here on my paper, and I don't remember what they all are. But what you're gonna do is you would take the difference here, right? The difference between the expected and the observed, and see which one it is. Now, and observed minus expected, okay? So that's all it's really looking for, is trying to show that it would be the biggest, what was the biggest contributing factor to coming up with your conclusion. And since we rejected the null here by saying that there is a difference in these colors, is want to know which one played the biggest part in that determining factor. And in this case, the other color key factor. So therefore, that's the biggest difference factor that played an effect for the calculation to actually put the numbers in favor of rejecting the null. And that's all it's really looking at there, or wanting you to observe. Other than that, it takes care of 11.1. That pretty much in a nutshell. Again, the big thing here is just taking away the big ideas, just as far as understanding the formulas to use, as well as the conditions, understanding that on this, you just got randomness you're looking at, and large counts, which is taking the lowest expected count, and multiplying it times your n value, your overall sample size, to see if that is greater than or equal to 5. And then really kind of understanding how to develop the hypotheses. It's dealing with your null hypothesis of saying that everything is going to be the same, and then your alternative, everything's different. And that takes care of pretty much all 11.1 for that setup there. All right, and that sums up everything you need to know for 11.1. Hope you learned a little bit of something today, and I'll see you next time.